digits, and our goal is for it to accurately classify each digit as a 0, a 1, a 2, and so on up to 9. That means we have 10 possible categories, making this a multi-class classification problem.
Oh, so we'd want to use the softmax activation function in the output layer then, right? Since it gives us those probabilities across all 10-digit categories.
Exactly. The softmax output would then tell us something like, I'm 95% sure this is a 7, 3% sure it's a 1, and 2% sure it's a 4.
Okay, but what about the hidden layers? Which activation functions will we use there?
Well, that's where we have some choices to make. We could use sigmoid or tan to squash those outputs, or we could go with the more modern and efficient RailU.
So the choice of activation function in the hidden layers really depends on factors like the complexity of the network and the type of data that we're dealing with.
Precisely. There's no one-size-fits-all answer here. It often just comes down to experimentation and seeing what works best for your particular problem.
I'm starting to appreciate the nuances of designing these neural networks. It's like we're building a custom machine, carefully selecting each component to optimize its performance.
That's a great way to think about it. And now that we've explored the world of activation functions, let's dive a bit deeper into how these networks actually learn from data.
Bring on the learning. I'm ready to see how those weights and biases are adjusted to make those accurate predictions. Remember backpropagation and gradient descent. Let's unpack those fascinating concepts. Okay, so let's revisit those terms that sounded pretty intense when we first heard them. Backpropagation and gradient descent. I have a feeling they're not as scary as they sound, though.
Yeah, you're right. They're actually very intuitive once you break them down. Remember how we talked about the network making predictions potentially having errors?
Uh-huh.
Well, backpropagation is all about learning from those errors.
So it's like the network is getting feedback on its performance and then using that feedback to improve.
Exactly. It's kind of like when you're learning to ride a bike. You might wobble and fall a few times, but each time you kind of adjust your balance and your technique based on what went wrong.
Right.
Backpropagation does something very similar for the network.
Oh, I like that analogy. But how does it actually work? My notes get into some pretty complex math here.
The maths can seem a little daunting, yeah, but the concept is pretty straightforward. Imagine the error signal flowing backwards through the network like a ripple effect.
Okay.
As the error signal passes through each layer, it helps us figure out how much each weight contributed to that error.
So it's like tracing the error back to its source and identifying the culprits.
Exactly. And once we know which weights are causing the most trouble, we can then adjust them to reduce the overall error.
And that's where gradient descent comes in, right? It helps us find those optimal weight settings.
Precisely. Remember that valley analogy from earlier?
Yeah.
Gradient descent is like taking small steps downhill, always following the steepest path until we reach the lowest point where the error is minimized.
So backpropagation identifies the problematic weights, and then gradient descent kind of guides us toward the best possible values for those weights. It's like a team effort to improve the network's performance.
You got it. It really is a beautiful interplay between these two concepts that allows the network to learn and adapt.
And my notes mention that this whole process happens iteratively, meaning we do it over and over again.
Exactly. It's not a one-time fix. We feed the network data, calculate the error, adjust the weights using backpropagation and gradient descent, and then just repeat the whole process. Each iteration helps the network kind of refine its understanding and get closer to making those accurate predictions.
It's like practicing a skill until you master it. The more you practice, the better you get.
That's a great way to put it. And that's really the essence of how neural networks learn, through this iterative process of feedback, adjustment, and refinement.
This whole deep dive has been incredible. We've gone from the basic building blocks of a perceptron to understanding how these complex neural networks can learn and adapt to solve all sorts of problems.
It's amazing how far this field has come, from those early perceptrons to the sophisticated deep learning models we have today.
And the applications are just mind-boggling. I'm thinking image recognition, natural language processing, self-driving cars, even medical diagnosis. It's like these neural networks are transforming the world around us.
They certainly are, and this is just the beginning. As we continue to explore the power of these networks, who knows what incredible advancements are waiting for us in the future.
To our amazing listener out there, thank you for joining us on this deep dive into the world of neural networks. We hope you've gained a newfound appreciation for the incredible power and potential of these technologies.
Keep exploring, keep learning, and who knows, maybe you'll be the one making the next big breakthrough in this exciting field.
Until next time, happy learning.